Alright, guys, in today's video, we'll be talking about the first section of the entire book of Calculus 2, and we'll be talking about part of the approximating area section. And before we even get to approximating or calculating areas under the curve, we have to lay out some fundamental concepts, some basic stuff to know before we get into details. And the first one that's very important is using the sigma or summation notation to calculate sums and powers of integers. Before we get there, one has to understand that people have been fascinated by a lot of things, and one of them being calculating areas or shapes of different kinds, squares, rectangles, triangles, and other irregular shapes. And one of the pioneers that was able to do a lot of research on that was Archimedes, which was from Syracuse, Italy. And he was a mathematician, physicist. He was an engineer. He was a lot of things. He did a lot of research on different principles and stuff. And when it came to calculating areas of irregular shapes, he used a method of exhaustion in which he would just take, let's say, a rock. Maybe let's say you have a rock of this irregular shape, and then you cut it into like small pieces of non shapes like rectangles, squares, or circles, or stuff like that. And then he'll calculate the areas using known formulas, and then he'll add them all up to get the total area. So like the way he did, then in this video we try to use his method by adding up small areas so that we can get the total area of the shape in question. So before we get there, though, let's first of all let's say we're trying to find the summation of 1 to maybe 10, right? We're trying to add 1 to 10, and then in your calculator or however you do it on the paper or something, you add it all up like that. So you're trying to just do normal addition, right? You can see that by writing it like this, it can just become tedious. Instead of doing that, maybe you can just save some time and write it like so. You can just become smarter and be like, okay, I can just avoid the numbers in the middle and maybe say 7 plus 8 to 10. You can see that it's still cumbersome, so you'll be wasting time still. So what if you come up with a better idea of writing it? You use a sigma notation, which is like basically a summation. I'm not good at writing it, but usually this is how mathematicians write it. And then you start with an index, and then you say, let's start from 1 all the way to 10, and then this a sub I will just be the number of terms you're trying to add up. What if you would just use this and then show that that's how you write it? That would be a better way of representing it instead of writing it this way, right? So when you use sigma notation, then you just save some time, and all these indices you see, they are just dummy variables. They can be anything, but instead of just wasting your time writing it the way I did it right here, you can just use this better, smarter way of writing things, right? But because we'll be dealing with a lot of different stuff, different addition, different variables, let's say you have a sequence of terms and you have other constants to add and stuff like that. I mean, what do you do when you are adding positive integers and they have different variables and terms to add? You gotta come up with some properties to memorize. So let's just start with some rules to follow, and we can just lay out some properties to memorize, and then after that, we can just have an example or two so that we can demonstrate what I'm talking about. So let me first start with writing down some properties down here, and maybe that you see what I'm talking about later on once I start uh, working on exercises. What C is just a constant. So it's like you just have a constant C, any number or anything that you are multiplying with a summation of things. And when you have that, you can just make it equal to NC. Gotta memorize that first. Then the second one will be then, let's just try to save some times and duplicate those things. So it'll be the summation of some constant C times a bunch of terms that we don't know. So if you multiply that with that, you can just make it equal. You can just move the constant to the front. All right. And then multiply with the rest of the stuff. So you can move the constant to the front. We don't need these here. We just need the terms, which will be a sub I. So that's the second property that we're gonna memorize. I know I keep giving you a bunch of stuff to memorize, but that's how math works. You gotta memorize a lot of stuff in order to understand or to make life easier, I guess. Let's see if we can duplicate this. And then kind of erase C because I don't need it. So what if then you had more than two terms, or maybe 100 terms? You gotta add some together. So this would be like, so this would be the first term right here, and this would be the second one. And then if you have 10 of them, they'll have different variables you assign to them, and then you add them all up. When you do that, you can just add them all up individually. You can just add one at the time, and you still get the same answer, right? You can just separate them out like that. And then you still get the answer. So that comes in handy sometimes when you are just adding up or subtracting a lot of stuff. So what comes next then? The next one will be subtraction. We did addition, now let's just do subtraction. So let's say you just have a bunch of terms you have to subtract. You can apply the same principles we just applied up above, and you still get the same answer, right? So just easy peasy for now. There's a bunch of stuff to add or subtract. That's it. And hopefully that makes sense. Yes. If you don't want to memorize all those things, just use common sense. It just makes sense. All right. Sometimes when you have like a whole number, a big number, you can just separate it out into two terms to make it easier. We can just do an example later on so that it will make sense. But and hopefully this makes sense to you. If it doesn't, there's always an open window for asking questions. And over here, you have to understand that all uh, these indices, mathematicians usually like to use I, J, K, M, N as indices. So that's what I'm doing right here. And they're usually, M is usually in between, is less than equal one. So 1 is less than equal to M, and then less than equal to N. So you are using that one. And then maybe so that you understand what I'm talking about right here, we can maybe prove, we can do some proofing. Maybe we can do 1 or 2, I don't know. Let's just do the proof of the second one. Maybe you understand what I'm saying. So if we are trying to sum a list of number, I don't know, it could be 20, it could be 100, I don't know, and we multiply it by a constant, right? We can just apply the commutative property or something, and then write it like that. Factor out a C, until we get to the last number. And you can see, if you were to multiply each one of them like that, right, it won't make a difference. You still get the same answer, right? You can also rewrite these like, so basically this can be rewritten. Actually, I should have started with maybe multiplying the constant with each term. Maybe that would make sense to some people. So this will be the first term, the second term. This should have been 1, second term, and then maybe we add a third term, because I don't want to write all of them. And then we get to the last term. And then you factor out a C, and you can see that this will be the same thing. This will give you the same thing, right? You can see that it'll be easier using this, right, than writing all these things out, because it's smarter that way. So as math people, we gotta just work in a smart way. Anyway, I just wanted to prove one of them. We don't have no time to prove all this, but those were properties of sigma notations. So basically, these are some rules or properties of sigma notation. Other things we have to memorize. Now we can move on to other properties for sums and powers of integers, right? For some reason I can't write today. All right. Sums and powers of integers, right? If you don't know what integers are, you gotta go back to algebra and stuff and understand rational numbers. And the rational numbers, they are fairly easy to understand. But these I'm about to write is just 3 of them, so it won't take us a long time. So let's start with the sum of some n integers that are given. So that is given by the following property that we gotta memorize, right? So basically, some people don't like memorizing stuff. But if you have a sum of the summation of a list of number, you gotta sum up, and it's just a sum of so let's say a given number of integers. Like we did earlier when we started up here. Let's say you want to add up 10 or 20. So instead of writing it like that, you can just do. So let me just write a little bit so that it makes sense, right? So you can just memorize this formula instead, right? And then just apply that formula instead. All right. So what if we had to add up some consecutive integers that are squared? What do you do then, right? So there's some other stuff you can memorize to make your life easier. All right. And I can't spell stuff today. Consecutive integers. And writing on the iPad isn't making it easier either. But we'll try. I'll make sure that you can read it. So the following property is then the one you use if you have a bunch of numbers that are in sequence and they are squared, and you have to add to add them all together. All right. So let's say you have a bunch of numbers you gotta square up, and it's a lot of them. All right. You don't have to make your life easier. You can just apply this formula and you make your life a lot easier. Okay. And these were like they came up with them using sequence and stuff, and something we'll cover later on. So you don't have to worry about it right now, but that's another property you're gonna memorize. Oops. And then the last one, if the numbers are cubed, you can also apply another property, all right? Basically adding numbers. There's nothing crazy about the stuff I'm writing. We're adding up numbers, and we are trying to understand, to use the sigma notation or summation method to add stuff up or subtract stuff up. All right. So nothing crazy here. We're just getting our hands wet a little bit. Later on, things will get a little bit hectic, but hey, it's not like it can be done. You've got it. You got this. All right. So let's see. So if you're adding a list of numbers, things that are cubed, all right, you can just use the following formula, all right? And this would be n squared plus n plus 1 squared divided by 4, actually. Let me highlight that as well. And that's it. Maybe now we can just do one problem or two, or maybe that'll start making sense. Let's just do a couple of questions. Let's just do exercise or something. Maybe that will make sense. All right. So let's use, all right, use the sigma notation to evaluate the following. All right, so let's see. So the sum of terms I, which is an index, it's like a dummy variable, so you don't have to worry about it. Could be anything, and we want I to be 1, 2, and add it all the way to 200. All right. So let's make this. Let's say solution. To do a solution, you can see that this, if you remember stuff from algebra, that's almost the same thing as a minus b squared. This can be rewritten as a minus b, all right, times. So if you don't remember what algebra says, you gotta remember about difference of squares and other stuff. And so if this was like a squared minus b squared, this will have been a plus b. Well, I should use all capital letters. It should be a plus b times a minus b, and this is what we are not dealing with this, so we are dealing with two of these. All right, so be a minus b again, and then you use the method of foiling, right? Hopefully you're paying attention in your algebra class or something. If not, oh well. If not, you see what I'm doing. I'm just foiling. So this will be then a squared. I'm just multiplying this with that one, right? And then minus ab, then minus ab plus b squared, right? So this will be a squared minus 2ab plus b squared. Now, since we are working in terms of i's and 3, so now we gotta use what we were given, right? So it'll be I minus 3 times I minus 3. And then we FOIL, right? Hopefully you were paying attention. And then this will be multiplied with that, and that will give us I squared minus 6 i's plus 9, right? Since we are using the summation notation, then this means if you are using I as an index and you are going from 1 to 200, this is how you'll be writing this. So it'll be summation of the first number. The first number is 1, and we are adding all the way to 200. And then the index, the number that we put here is this squared, right? So this will be like a sub I, right? So this will be then, rewrite that again, and then we bring this down here, right? Because they are the same thing. We've established that this, let me use a different color. We've said that this is the same thing as this right here. That's the same thing as I minus 3 squared, right? Which is equivalent to that. So then we have to bring that down here. Let's duplicate it because I don't want to write it. All right. So that's what we are working with right now, right? Now that we have that established, we can separate them out and then apply the properties that we gotta memorize, right? So this then will be the summation of I equals 1 to 200 of I squared minus the summation of 200 I equals 1. I mean, the summation of 1 all the way to 100. That's the proper way of saying it. And then plus summation of 1 all the way to 100 of 9, right? So now we have some properties now to use, right? So this one, let's use a different color. Oh, that's messed the whole thing up. So let's use this color, maybe bright color, and this, right? Okay, let's go back to the pencil. We have a property that says if it's squared, where did I put those properties? Okay, right here. So you can see if it is squared, you gotta use this formula, right? So we have I that's squared, so let's go down here and use the property then, right? So we can just grab it and copy it or duplicate it, if whatever you want to do. Put it right here to the side and then apply it here. So this will be then the summation of because I have to fix certain things before I apply that rule. Because we have a constant right here, I want to move it to the front. Okay, so this will be I squared minus 6. I'm moving 6 over here, and then times summation of 1 all the way to 100 I plus the last one will remain the same, so we can just copy it, put it there, and now we can now apply that formula. So this then will be 200, which is n, because remember when we were doing the sigma notation, we said that that's n, right? So n will be 200, right? And then n plus 1, which is 200 plus 1, and then times 2n, so 2 times 200, right? So 2 times 200 will be 400, right? Plus 1 divided by 6, right? And then let's see if I can move stuff around, because I'm running out of space, right? And then minus 6 times, so we said if we have this, right? Let me use the highlighter so that it makes sense, I guess. If we have this, we can use another property, which is this one right here, right? Because that's what we have right here. Okay, so n times n plus 1 over 2, right? So which would be then 200 times 200 plus 1 divided by 2. All right. And then plus 9 times 200, right? 9 times 200, where did that come from? Another property, yeah, right here. This is, let me use the highlighter. This is another property we are using right there. Okay, so that's where that's coming from. Okay, and we get, when you put in the calculator, let me get my calculator really quick. Okay, what? 6. Okay. That will turn into 2,500,679,000. Okay. And that's all you get. That's the answer. All right. And for the sake of time, maybe let's do another one, another exercise, and then maybe we'll be done with this video. All right. Let's see. Let's evaluate this summation right here. Okay, so we can separate that out again and just use the properties, right? We're gonna memorize like I said earlier, and it become easier that way. My bad. This is a subtraction, not an addition. All right. When it's cubed, you have to pay attention to this. Cube, square. All right, so we know the square one is this one, and we have the cube one up there. That's what you have to bring down here, and then the problem is done. All right, so this will be then the if n squared times n, which is 6 plus 1, all the whole thing squared, and then divided by 4 minus n, which is 6 times n plus 1, times 2n, which is 2 times 6, and that's 12, plus 1 divided by 6. Oh, that be my dandy calculator right here. Let's get our dandy calculator. Oh, come on. Okay. So that would be 6 squared, 36, times 7 squared, 49. So 49 times 4 is 36. So 1,764. Okay. Divided by 4 minus, there's the second one, 6 times 7. Okay. Times 13. Okay. So 546 over 6, and then we find a common denominator, which will be, I guess 24, I guess 24. And then you do all that, and then you get 355. Okay. All right. Thank you very much for your interest in this video. The next time we'll be doing some fun stuff about approximating the area under the curve. We'll be adding a bunch of rectangles from the left or right side of the curve or something, and then we'll just come up with the area under the curve. All right, thanks for watching. Bye-bye.